Good afternoon. My name is Fabio, and I will present to you Chapter 7 overview along with my partner Donovan. So to start with chemical equations and mole ratios, chemical equations describe chemical reactions that consist of elements and compounds reacting to change their chemical makeup. So there's two components to chemical equations: the reactants, which are the elements and compounds which we start with and react, and the products, which is a result of the reactants reacting, and that's changing chemical makeup. Also note that their mass is always conserved. So let's say you start with 2 moles of carbon, you have to end with 2 moles of carbon. So let's go do some examples of balancing some chemical equations. So for the first one, we have carbon dioxide reacts with hydrogen to create methanol. So first we're going to start with the unbalanced form. So we see we have carbon dioxide plus hydrogen leads to methanol and water. And we went ahead and added the symbols for their states of matter, and then when balancing it, we have to observe how much we have of each atom, and we can go one by one. So for carbon, we see we have 1 carbon on the reactant side and 1 carbon on the product side. So we're good there. Mass has been conserved. So then we go ahead and move on to hydrogen. So we have 2 hydrogen atoms on the reactant side, and 1, 2, 3, 4, 5, 6. We have 6 on the product side, so we're gonna have to balance that out. So to balance it out, we could go ahead and go to the reactant side, which has less hydrogen atoms, and add a coefficient of 3. And what happens is that by adding a coefficient of 3, we're adding more hydrogen atoms. And this gives us 6 hydrogen atoms on the reactant side and 6 on the product side. And then we go ahead and take a look at oxygen, and we have 2 oxygen atoms on both sides of the chemical equation, so we're good there. Also, keep in mind that the coefficients represent how many moles there are of each atom or molecule. So our mole ratio is going to be 1, 3, 1, 1, since we have 1 mole of carbon dioxide reacting with 3 moles of hydrogen, of the diatomic molecule of hydrogen, reacting to produce 1 mole of methanol and 1 mole of water. All right, so let's go ahead and look at a second example, this time being methanol combustion. So the unbalanced equation is right here is the first one. It says methanol plus the atomic molecule for oxygen leads to carbon dioxide and water. So we're going to start by looking at the carbon on each side. So we see we have 1 carbon on the reactant side and 1 carbon on the product side. So we're good there. Then we look at the hydrogen, and we notice that we have 4 hydrogen atoms on the reactant side, but only 2 on the hydrogen side. That means we're going to have to add a coefficient of 2 to the H2O, the water, on the product side in order to have the same amount of hydrogen atoms. And this messes up our number of oxygen atoms. So when we go ahead and look at the oxygen atoms that we have, we see that we have 3 on the reactant side, and we had 3 on the product side, but once we added the coefficient, we now end up with 4 oxygen on the product side. So we have 3 in the reactant and 4 in the product. So to make that work out, we can go ahead and add a coefficient of 3 to the oxygen on the reactant side. And we can also go ahead and add a coefficient of 2 on the methanol, also on the reactant side, in order to get an even number of oxygen. And that's going to give us 8 atoms of oxygen on the reactant side. However, now we have more carbon and more hydrogen. So we can fix this by adding a coefficient of 2 to the carbon dioxide on the product side, and changing the coefficient from the water from 2 to 4. And this way we get an equal amount of atoms for all of the atoms in the products and reactant sides for the combustion of methanol. Moving on to mole ratios. Mole ratios relate how many moles of each atom or molecule in a chemical reaction are needed for the chemical reaction to go through, and these are used to find out how much of a reactant is needed, or how much of a product is made. And then let's go through some examples. So for the first example, we ask ourselves, for every mole of methanol produced, how many moles of hydrogen are needed? So we already have our mole ratio, and we see that for every mole of methanol produced, we're using 3 moles of hydrogen. So that means we need 3 moles of hydrogen for every methanol produced, and that's how we can relate the mole ratio to how much is needed. And then for the second example, we ask ourselves, for every mole of methanol combusted, how many grams of water are produced? So this applies to our second example when discussing balancing chemical equations. And we start by remembering that the mole ratio is 2 to 4. And then we go ahead and get 1 mole of methanol, and you can multiply that by 4 moles of water over 2 moles of methanol, since that's the ratio. And then we go ahead and multiply that by 18 grams of water over 1 mole of water to convert to grams. And then that gives us 36 grams of water, and that's how much water we're going to need. Now let's discuss limiting reactants, theoretical yield, and percent yield. So what is the limiting reactant? So a limiting reactant is a reactant in a chemical reaction that is consumed completely and is consumed first. And it's limiting because it limits the amount of product made since the first reactant consumed. So let's go ahead and look at an example. So we're going to use the chemical reaction for producing methanol used in the previous slide. So the question asks, if we are trying to produce methanol, we have 47 grams of hydrogen and 40 grams of carbon dioxide, which is a limiting reactant. So to see which is a limiting reactant, let's go ahead and calculate how much of the product, methanol, we can create with each amount of the respective molecules. So for hydrogen, so we go ahead and start with 47 grams of hydrogen, and we're going to multiply it by 1 mole of hydrogen over 2 grams of hydrogen in order to convert to moles. Then we go ahead and multiply this by the ratio that we had from the previous slide, which is 1 mole of methanol for every 3 moles of hydrogen. So when we do this, we calculate that we can produce a max of 7.76 moles of methanol with 47 grams of hydrogen. So now let's compare this to carbon dioxide. So for carbon dioxide, we have 40 grams of carbon dioxide. We're going to multiply that by 1 mole of carbon dioxide over 44.01 grams of carbon dioxide, since we have to convert to moles first. And then we can relate it to the ratio, which was 1 mole of methanol over 1 mole of carbon dioxide, and that gives us 0.99 moles of methanol. So with this, we can see that we can produce much more methanol with the hydrogen we're given if we have an infinite amount of carbon than the other way around. So this means that carbon dioxide is a limiting reactant, since we could produce much less with the carbon dioxide with that amount. So let's go ahead and move on to theoretical yield and percent yields. So the theoretical yield is the max amount of product that could be made if the reactants are used up completely. And the percent yield is the actual yield divided by the theoretical yield, and then we times that by 100 to convert to a percentage. And then usually the actual yield is lower than the theoretical yield due to a lot of outside factors, such as the reactants not reacting completely with each other. Let's take a look at the first example. It asks, let's suppose we have an infinite amount of zinc, but only 50 grams of hydrochloric acid. What is the theoretical yield of zinc chloride in grams? So I went ahead and wrote down the chemical equation. And then, so for the theoretical yield, so we start with 50 grams of hydrochloric acid. We want to know how much zinc chloride can produce. So we multiply that by 1 mole of hydrochloric acid divided by 36.46 grams, since we have to convert to moles before relating the hydrochloric acid to the ratio. So the rate, and then we go ahead and multiply by the ratio, which is 1 mole of zinc chloride produced for every 2 moles of hydrochloric acid. After that, we multiply it by 1 mole of zinc chloride divided by its molar mass, since we have to convert back to grams, since the question asked us to do so. And then we get 93.45 grams of zinc chloride. And this is a theoretical yield. So now the next question asks, what we did the experiment with those same amounts of reactants, but only ended up with 75.50 grams of zinc chloride. What is the percent yield? So the actual amount we got was 75.50 grams. So we divide that by the theoretical yield, which is a max amount possible. And from the previous question, we got that was 93.45 grams. So we go ahead and divide those, and then we multiply by 100, and we get the percent yield to be 80.79%. So we only ended up with 80.79% of the max amount of zinc chloride that could be produced with the reactants we had in our disposal.
Now we will be discussing percent composition by mass. So to find percent composition by mass, we will be using the formula molar mass of the element times the subscript of the element divided by the molar mass of the entire compound times 100%. So for example, we must find the percent composition by mass of CO2. So first we must find the molar mass of the entire compound. So we know that carbon is 12.01 grams per mole and oxygen is 16 grams per mole times a subscript of 2. So we add those together and we get 44.01 grams per mole. Now we can start finding the percent composition for each element. So let's start with carbon. So carbon is 12.01 grams per mole, and there's only one. So we will simply just divide 12.01 by the molar mass of the compound, and we will get 0.2729. And then we multiply this by 100 to get the percentage, and we get 27.29%. Now for oxygen, it's the same steps. Oxygen is 16 grams per mole times a subscript of 2. Then we divide that by 44.01 grams per mole, and we get 0.7271. And then we just multiply this by 100 to get the percentage, and we get 72.71%. So CO2 is 27.29% carbon and 72.71% oxygen. Now we will be discussing how to find empirical formula and molecular formula using percent composition. So to do so, we'll be following the steps shown in the bottom right. So for the example we know that the molecular weight of a compound is 180.16 grams per mole, and it contains 40% carbon, 6.71% hydrogen, and 53.29% oxygen. And what are the empirical and molecular formulas of the compound? So first we can assume, since that we have a percentage, that the total mass of the sample is 100 grams, and this allows us to make carbon 40 grams, hydrogen 6.71 grams, and oxygen 53.29 grams. Then we convert from grams to moles, so we multiply 40 grams of carbon by 1 mole over 12 grams, and that gives us 3.33 moles. And we have 6.71 grams of hydrogen multiplied by 1 mole over 1.01 grams, which gives us 6.64 moles. And then we have 53.29 grams of oxygen multiplied by 1 mole over 16 grams, which gives us 3.33 moles. So then we divide all of these by the smallest mole. So in this case, it'll be 3.33 moles. So for carbon, 3.33 divided by 3.33 is 1. Hydrogen, 6.64 divided by 3.33 is approximately 2. And oxygen, 3.33 divided by 3.33 will be 1. So this gives us an atomic ratio that we can use to find the empirical formula. So now we can calculate the empirical weight using this empirical formula. So carbon is 12 plus 2 hydrogens, which is 2, plus 1 oxygen, which is 16. So we have 12 plus 2 plus 16, and we get 30 grams per mole. Then we divide the given molecular weight by the empirical weight. So we'll have 180 grams per mole over 30 grams per mole, and we get 6. So then we multiply this 6 with the empirical formula CH2O, and we get the molecular formula C6H12O6. Finally, we will discuss how to find empirical formula from combustion analysis. So combustion reactions generally look like this. So we have a compound made up of carbon, hydrogen, and oxygen that will react with oxygen to form CO2 and H2O. So we will be finding the mass of carbon from CO2, the mass of hydrogen from H2O, and the mass of oxygen in the original compound by subtracting carbon and hydrogen. So for our first example, there is 14.77 grams of a compound that produces 43.26 grams of CO2 and 12.4 grams of H2O, and we must find the empirical formula. So first, let's start off by finding grams of carbon from CO2. So we will do this by converting grams of CO2 to moles of CO2, which we can use to find moles of carbon and then convert to grams of carbon. So we have 43.26 grams of CO2, and we multiply by 1 mole of CO2 over 44.004 grams of CO2 times 1 mole of carbon for every 1 mole of CO2 times 12.011 grams of carbon over 1 mole of carbon, and we get 11.81 grams of carbon. Now to find hydrogen from H2O, we'll be following similar steps. So we have 12.4 grams of H2O times 1 mole of H2O for 18.015 grams of H2O times 2 moles of hydrogen over 1 mole of H2O times 1.0079 grams of hydrogen over 1 mole of hydrogen, and we will have 1.388 grams of hydrogen. Now we can find grams of oxygen in the original compound by subtracting hydrogen and carbon. So we have 14.77 grams of the original compound minus carbon, which is 11.81 grams, and hydrogen, which is 1.388 grams, and we get 1.57 grams of oxygen. Now, if we want to find the empirical formula, we must convert to moles and divide by the smallest mole. So we have first for carbon, 11.81 grams of carbon times 1 mole of carbon over 12.001 grams of carbon, which gives us 0.9833 moles of carbon. Then we have 1.388 grams of hydrogen times 1 mole of hydrogen over 1.0079 grams of hydrogen, and we get 1.377 moles of hydrogen. Then for oxygen, we have 1.57 grams times 1 mole of oxygen over 15.99 grams of oxygen, which will give us 0.0981 moles of oxygen. And then we divide all of these by the smallest mole, which is 0.0981. So for carbon, we have 10, hydrogen we have 14, and for oxygen we will have 1. So that will give us C10H14O1, and that will conclude our project. Thank you for listening.